Lab 5, Falling Magnet by Colin. The purpose of this lab is to observe the effects of Faraday's law and try and model the physical properties with GlowScript. The concepts are Faraday's law, the Biot-Savart law, Newton's laws, Ohm's laws, the B field force on a loop, as well as magnetic flux. The equations are shown on the right. The results of this experiment is that the experimental time of the magnet falling was in 1.96 seconds, while the computational time was 1.89 seconds. The assumptions are that the magnet falls perfectly straight, there's no air resistance, and gravity and the magnetic force are the only forces acting on the magnet. The system is the magnet in the tube, and the surroundings are the universe. The observed data shows that the average time of drop is 1.96 seconds. The length of the tube was 45.5 centimeters. The width of the foil was 0.01 meters. The inner radius was 0.015 meters. The magnet mass was 0.12 kilograms. The magnitude of the mu value was 3.089 am squared. And the average time was 1.96 seconds. The GlowScript code shows the starting conditions as well as the calculation for the dipole of the B field and calculating the flux over dt. These calculations were used in a loop in order to calculate the position of the bar magnet and the velocity of the bar magnet in iterations using the d flux over dt as well as the B field on the magnet. Calculating current and the force due to gravity and the force due to the magnetic field. The simulated results show a constant velocity after the magnet initially drops down and the magnetic field kicks in to counteract the gravitational force. And then once the magnet has left the tube, it accelerates again. The results show that the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. The blue shows the clockwise and the red shows counterclockwise. When you flip the magnet around, the system acts in the same way, but the blue and the red color will switch. The total time in tube of the real-world system is slightly longer, most likely due to human error in timing. The computational system is likely as accurate or more accurate than the timing of the real-world model. Some sources of error: human error in measuring the drop as well as timing the drop, and inaccuracies from Lab 3 of the mu value. What if the resistivity of the conductor were reduced as close to as possible to zero? How would the dynamics of the falling magnet change? It would greatly decrease, if not completely stop, the fall of the magnet due to Ohm's law, because V is equal to IR, and so as the current decreases, the resistance increases greatly, and the force of the magnetic field would increase. If there were holes or slots in the tube, this would decrease the contribution of magnetic force from the aluminum onto the magnet because it's decreasing the amount of aluminum in the tube, which would allow the magnet to fall faster. In conclusion, this lab accurately modeled Faraday's law and the effect of magnetic force on a falling magnet created by an induced magnetic field.